So my title today is Typed Program Analysis Without Encodings. And I really enjoyed the Brigitte's talk, but I'm not smart enough to do that kind of stuff, right? So we have a lot in common. We're doing typed program analysis. Brigitte was saying that metaprogramming is programs that produce programs. And I think that's right. But isn't that what higher order programming is supposed to do? Yeah. So the thing that makes us different is that I want to do away with the encodings. No quotation. Yeah. On a couple of the slides, Brigitte had the extensional side and the intentional side. And that's the key, because lambda calculus and our lovely favorite functional languages and the rest don't do intentionality. And that's where all the problems start. So I want to show you today a calculus where intentionality is first class. It's baked in at the beginning, and so everything's become simple enough that I can understand. Right? Yeah. So at the heart of all of this is the idea that programs have a dual nature. On the one hand, they're functions. They take inputs, they produce outputs, and we often think that that's their primary nature. But if we're doing a partial evaluation, program manipulation, metaprogramming, well then we want to think of them as data structures on which we can do pattern matching, that we can manipulate them and change them in that way. So how do we reconcile these two natures? One is to introduce a meta theory of quotation, boxing and unboxing that gets us back and forth. But now, what happened to the idea that there's only one notion of computation? The Church-Turing thesis says there's only one way, one kind of computation. How come we suddenly have two? Yeah. So that's a bit unsatisfying. But the usual approach is to say, oh, our programs are functions, and we'll do this quotation to get out some syntax. But we can turn that around. What if we say, oh, let's take the data structure as the primitive thing. How can I impose some functionality on that? Well, the answer is do some algebra. You add some equations to explain how those things work. Yeah, so if we look at combinatory logic with its operators S and K, then we can think of the things like this S, X, Y, Z. We can think of that as a syntax tree. It's got a root labeled by S and three branches, X, Y, and Z. Yeah? And when we want to manipulate that and evaluate it, then we end up with a new syntax tree where we're attaching branches to the root of X. So we have this working already. So why don't we go that way? Whoop, I seem to have. Right. Well, the biggest argument is that these operators, S and K, are artificial. I might want to add in an identity operator or some other B's and C's and whatnot, yeah? But since there's only a finite alphabet, each of the letters, S and K and the rest, can themselves be represented by small trees without any labels on them. So we can take any syntax tree in any language and replace it by an unlabeled tree. Well, these unlabeled trees are natural things. Just as the numbers are natural and can be represented by beads on a string, these natural trees are also well-formed semantic objects. Yeah? Nothing human about them, nothing artificial. They're natural. Yes? So now we can say, okay, our programs are going to be unlabeled trees, natural trees. What kind of equations, what kind of algebra do we want to put on those things? Well, if you think that this little subtree represents S and this one represents K and so on, you can write some complicated algebra to describe their behavior. But now that we understand that we're working with these unlabeled trees, let's start over. Let's start fresh. So the nodes, these unlabeled nodes, represent a single operator. Instead of S and K and the rest, these unlabeled nodes are the unique operator, and I like to think of Leibniz and his notion of monads, that everything in the world is built out of combinations of a single monad, yes? Well, it turns out you can write some nice rules for these things, and you can build some interesting trees and do some interesting computations. Too many fingers again, right? So here is the frontispiece from my book. It seems to have it's not. You can guess what's at the bottom, yeah, but. Well, I don't imagine anybody's going to pass this thing exactly, but you can build up interesting trees. This here is a self-evaluator, an eval in the sense of a meta computation. Yes, so this really is a working program, and we don't need any encodings because it can be applied to itself without any meta theory. Yeah, I'll just take a moment to describe how this tree works. The colors are not part of the semantics. They're there to help us, yeah. But this green bit at the top does the recursion. And this red bit here does the case analysis. And if we keep going down, you can see 3 green branches. 1, 2, and there's a tiny little one there. Those are the 3 branches of the pattern matching function. I have 3 branches because all of my data structures, all of my values are binary trees. So either they're a leaf with no branches, or a stem with 1 branch, or a fork that has 2 branches. So I need 3 cases in my pattern matching function. And of course, when you're doing evaluation, you impose a strategy. So this is a breadth-first strategy for working over the trees, something like an eager evaluator. And this red bit at the bottom, that is the eagerness. That's the strategy. Yeah? So all of this goes rather directly. And this is the subject of a book I wrote after I retired, called Reflective Programs in Tree Calculus. Yeah? So I built all of that up. That was the key ideas were done by 2019, and nobody would accept it for publication. So I got a book contract and I wrote the book, but then the publisher couldn't find anybody to write a review. Yeah, it's too crazy. Yeah. So a friend said to me, look, I don't really care about self-evaluators, that's boring, but if you could do a typed one, that would be really cool. Yeah. So in 2021, I said, okay, how long can it take, right? And now here in 2025, I want to show you a type system for this this calculus. Yeah. Well, before I get there, I should say that there's actually at this stage 2 variants of tree calculus. Everything I've said till this moment is the same for both of them. The original one in the book gave the tree that's there. And the goal was to have just 3 reduction rules, 1 for leaves, 1 for stems, 1 for forks. And I did some trickery to make that work. Well, Johannes Bader has been, we've been in conversation for a year or so now, and he's been keeping me honest and making useful suggestions and things. And he said, but it'd be so much simpler if you just used 5 rules. And I'm going, 5? That's a big number. You go, no, it'd be simpler. So these days we're working with triage calculus, and here are the 5 rules. So the first one, so this node operator is a ternary operator, and it's intentional. It looks at the structure of its first argument. So if the first argument is a leaf, then you take y and z, return y. This is just like K of combinatory logic. It deletes something, yeah? And if the first argument is a stem, then it copies something, just like the S operator of combinatory logic, yeah? So in these first 2 lines, we have all the power of combinatory logic. That is to say, all the power of lambda calculus, the ability, Turing completeness. We can do all the arithmetic, yeah? But there's more, right? So we can ask, what if the first argument is a fork? Well, if that's the case, then by the time we get to when we look at the first this fork here, the program, then there are three subterms, W, X, and Y, and they will provide the cases for the pattern matching. So now we're going to analyze the third argument. If it's a leaf, then we use the first case of the pattern matching, we use W. And if it's a stem of U, then we use the second case, X, and we apply that to U. And if it's a fork of U and V, then we take the third branch of the pattern matching Y and get YUV. Yeah? So these last three rules here are called triage, which is a pun on the tree calculus and the fact that there are three kinds of values. Yeah? And that was a rather elaborate construction in the original tree calculus, but now it's just baked into the reduction rule. So everything becomes a bit simpler. Yes?
So these triangles are ternary.
Yes.
You probably need to repeat my question.
The triangles are ternary, yes. Ternary operator.
Ternary operator, but the inner pattern match you have there, you only have the case of a triangle that takes two arguments. You don't have the one where it takes three.
Right. This is a combinatory calculus. So when I say a ternary operator, it can be applied to 0, 1, or 2 arguments without any reduction. When you apply it to 3 arguments, then reduction rules apply.
So if I understand correctly, is this working?
a monad or a combination. Here, every program is either a leaf or it's an application. So I just need two type derivation rules for those things. But I'm going to use subtyping to gain expressive power. So whenever the leaf type is less than some type t, then the leaf node has type t. And application rule is just the usual thing. So you've got a bog standard rule for application, and leaves have type, nodes have type leaf or some supertype of the leaf type. So all of the expressive power is focused in on this subtyping rule. Yeah. Well, if we're going to turn leaves into stems by application, then it better be the case that the leaf type is less than a function type. And the obvious thing, at least obvious if you have a moment to think about it without some guy rabbiting in your ear, the obvious thing is that if you get a branch of type U, then leaf applied to that will produce something that's a stem with a branch of type U. So there's how to turn a leaf type into a function type. In the same way, if we have a stem of type U and we apply that to a branch, we want to get a fork. So stems are a function type into fork types. So now at least we can build up our binary trees from leaves. Okay. Well, we've got function types there, so we better do the usual thing with those. They are covariant in their result types and contravariant in their argument types. And this is enough to give us subsumption. Even though our subtyping is focused on the leaves, we are able to get subtyping to apply quite generally. We don't need a special rule for that. By focusing all the subtyping on the leaf types makes the proofs a lot easier. Yeah. Well, we've got started, but what are we going to do about the reduction rules? Well, it turns out that each of the reduction rules inspires a subtyping rule to relate the left and right-hand sides of the subtyping. So if we have a node applied to node and some x and some y, well, the node x becomes a fork of a leaf and something. When we apply it to some other v, we toss the argument of type v away and keep the argument of type t. Yeah. So this is the k reduction rule of tree calculus. The information in that rule is captured in this subtyping relation. Yes. The second rule, if you're captures the properties of the S combinator. If you're familiar with the S combinator, you see here's the arguments of type u to v to t and u to v, and the result is of type u to t. So if you've done any combinatory logic, then this will all be a bit familiar. The F and the S are used to build up the type of the left-hand side from the types of the arguments. And in the same way, with a little bit of thought, you can produce rules for triage. Yes. So I'm not sure that staring at them for another 30 seconds is going to make it much clearer, but each of the reduction rules inspires a typing rule, right? So from this, we can see that k is of type u to v to u, S has its usual type, and you can define the identity in terms of k and s, it gets its normal type. So all of the things you do in simply typed lambda calculus or combinatory logic are all working as expected, yeah? So what about recursion? What about fixed point functions? Well, in lambda calculus, recursive functions don't have normal forms. Yeah, y of f can reduce to f of y of f, and there's no way of getting around it. Yeah, but in tree calculus, all of our programs have to be binary trees. They have to be normal forms. So what's going on there? Well, the interesting thing is that although we traditionally think that all these models of computation are equivalent, they're not equivalent in some interesting ways. So in combinatory logic, every combinator is equivalent to one in normal form. And the reason for this, I haven't prepared a slide on this, but if you think about the eta expansion, that m goes to lambda x mx, and then you do a very naive interpretation of the lambda abstraction back into combinators, it splits apart every application in the original argument m. So every combinator in combinatory logic is eta equivalent to one that is in normal form. So in lambda calculus, there's no escape the fact that fixed point constructions have no normal form, but even in combinatory logic, we can do that. And we use the same kind of tricks here. And the heart of it is this weight operator. So in combinatory logic or in tree calculus, you can define an operator. So weight2 says, give me 4 arguments, and then I'll do something. If you only give me 3 arguments, then I'm going to wait till I get another one. Yeah? So that's this decomposition process played out. So now we can define a fixed point operator z as a weight, and we have to massage the usual account of fixed points to take account of weighting. But now we get a fixed point construction which is in a binary tree, which is in normal form, and that's all good. So if we think about trying to type that thing, now we're going to use the fact that every program has a tree type. So if you think about this little omega from the previous slide, it has a tree type that has exactly the same structure. And if we want to give a type to the fixed point functions, just in the same way that we used our knowledge about the reduction rules to do subtyping there, we can use our knowledge of the correctness of the fixed point construction to add a subtyping rule that reflects that. So here's the subtyping rule that supports typed recursion. So omega 2 is just a tree type, but it can be thought of as a tree type from itself to the type we need for building fixed points. So if you think about self-application in a fixed point construction, or omega applied to omega, that's captured here by the subtyping rule. So the motto of the system is that the term language is going to be fixed. It's just these binary trees. But if we want a more expressive type system, we don't hack the term language. We don't add in let terms or boxing or new kind of variables or type applications or whatever it happens to be. There aren't 1,000 versions of tree calculus. Yeah? Instead of hacking the term language, we're going to hack the type system. And the thing we have to hack the most is this subtyping relation. But whenever you give a proof that some term has some nice property, that given an argument of a certain type, the result will be a certain thing, then my experience is that can always be encoded as a subtyping rule. That's how you improve the expressive power of the system. So in this talk, I'm going to show you 3 examples of this kind of hacking to get things done. Yeah, so that's fixed points. So now we can type all of the mu recursive functions on natural numbers. Yeah. Again, Brigitte and I are both talking about the size function. Yes, and it's a pattern matching function. Yes, so in pseudocode, we can say that the size functions of the size of a program P, well, if it's a leaf, then the answer is 1. If it's a stem, it's 1 plus the size of the branch. And if it's a fork, it's 1 plus both of the sizes. Yeah. Well, triage captures this. Here is the same program written out. The Z is the fixed point. Then we take an argument. There's a recursion argument, and then we do the triage, and there's the size program written in tree calculus. Yeah. What about the typing? Well, if we look at the type of the tree type of that program, at the heart of it is this fork type. So the triage has got 3 branches. It's the fork of a fork. And the first one is the number 1, which is of type nat. And the second one, I've just thrown in quantified types without telling you. That was in the ... earlier, right? But the second argument will produce a nat from 1 argument, and the third produces a nat from 2 arguments. So we have to turn this into a subtype of the expected type of size, which says, given 1 argument, any argument, give me a nat, right? We could just make this a subtyping rule and everything would be fine. But in fact, size is just an example of a generic query. We can write generic queries for equality or looking for a subtree of a certain shape or whatever it happens to be. So we can generalize this rule. We need to have the notion of covariance to take care of things. But the general form of the rule for generic queries says if the branches for leaves, stems, and forks are all coherent in some sense, then if we can type what's happening on leaves and stems and forks, then we can type everything. So the notion that every value is a binary tree gets encoded up into this rule. It's a little bit heavy to write down, it's in the paper, it's in the book. Not the book doesn't do any types, but you've got the spirit of it here, yes? We've written a subtyping rule that captures the notion that every value is a binary tree. Yeah. Well, the third example today is a self-evaluator. It's called BF because it does breadth-first evaluation. You never evaluate a node until all of its branches have been evaluated. Yeah, and it's a pattern matching function. It's given a program f, a function f, and an argument a. You look at f. If it's a leaf or a stem, then you just immediately build the data structure, the stem or the fork that comes out. If itself is a fork, then you have a look at what z is, and if the program is actually k, then you return y. If it's a stem, then you have to evaluate xa applied to ya. And here's the function eager that I mentioned earlier, which is ensuring that bfya gets evaluated before you evaluate the rest of it. Yeah, and then you just follow your nose, take the naive account of what a breadth-first evaluator should do. It comes as a pattern matching function, and then you can encode that as a tree. Yeah. So here it is written again in more formal kind of tree calculus. When it comes to typing this thing, we end up with a conditional typing. If this fork type FUV can be a function type, then we can get a function type for this other argument. Well, I didn't want to do conditional typing. I'm not smart enough. Yeah. So I hacked the type system again and introduced this type constructor A, which is as function. So it stops anything happening to that type until it proves to be a function type, and then the obligation's discharged. So doing things that way, we can give a type for, and adding some new subtyping rules, we get a type for BF that takes any Z and produces an A of Z. When you specialize Z to a function type X to Y, we get this very elegant type for the breadth-first evaluator. It takes a function and an argument and returns something of the result type. Yeah. So this is working in system F plus some tree types. Not system F omega, not system F omega with some tower of expression types and boxes and things on top. It's just a slight extension of system F, yes. So using triage types, the breadth-first evaluator shrinks. And Johannes was very keen to make this thing smaller, and he kept saying, I've got a smaller tree for the breadth-first evaluator, and then I had to go back and rehack the type system. Yeah, so he was, cracking the whip there, right? Anyway, this self-evaluator has 392 nodes. Yeah, Johannes has one now at 352 nodes, but I can't type it. not yet. So, so that's the story there. I have a slide about the church Turing thesis, but since the chair has stood up, I'm thinking, ask me a question if you like, and have some conclusion stuff. But should I go through the conclusions or stop now?
Yeah, and it's already 3 minutes over.
Oh, excuse me. Right. Okay.
Yeah, thank you very much.
Yes.
Very quick one. Well,
I can just speak back.
yeah.
It needs to be in the mic so that I see.
I was just curious if the tree-based structure allows you to do any special graph theoretic properties, or if it's more of a conceptual conceptualization for the user.
The tree structure is there because I want to have a single operator. So as soon as I commit to a combinatory calculus, I've committed to the trees.
Gotcha.
Yeah?